So we've seen how to personalize recommendations by either grouping users according to their past ratings or by grouping items according to the past ratings they have received. I mentioned briefly that the item-based personalization is better in practice. However, there's something that's potentially even better. Combining both approaches into one recommendation algorithm that's both item and user-based. There might be something very specific about why Frank likes Dirty Dancing that comes from both the fact that he's Frank and the fact that the movie is Dirty Dancing. It's the user-item combination that really matters here. To see how we can leverage this rough idea, let's go back to our geometric picture. Remember, when we talked about user-based recommendations, we thought of users as being clusters in some space. In the case of user item-based recommendation, this is also the kind of picture that we need to see. However, it does not take place in the same space. We need to find a space where we can see the pairs of user items. This is the picture we had for user-based recommendations. This idea is nice in principle, but it looks great only in two dimensions, the x-axis and the y-axis. In reality, this picture takes place in a very high-dimensional space. It has as many dimensions as there are movies, about 17,000. And there is one problem. It becomes difficult to measure similarities accurately in high dimensions. Recall that each user, for example Frank, can be seen as a row of lengths 17,000, which represents all Frank's potential ratings for all the movies in the database. We have seen that the similarity between two users is measured by the inner products between their rows. Let us look at the most central user we can think of, the user that rates all movies a 3, the average rating. Next, assume that all other users are variations around this central user. Their ratings for each movie are as follows. With probability 1/2, they rate the movie a 3, like the central user. But with probability 1/4, they rate the movie a 4, 1 point higher than the central user, and with probability 1/4, they rate the movie a 2, 1 point lower than the central user. We can represent each new row as the sum of a row of 3s for that central user and a row that contains only 0s, 1s, and -1s. Let us call the first row C for central and the second row D for difference. Now let us look at the inner product between two such rows, C plus D and C plus D prime, where D and D prime are two separate different rows taken independently at random. Let's run some simulation to see the similarities between such users. This plot is a histogram of inner products between all pairs of 10,000 rows of the form D inner product with D prime for D and D prime random. We can see from this histogram that most of the inner products are between -200 and 200. This range is not very large, so inner products between users from the central's cluster should sit close to the inner product between the central user and itself. This is 3 times 3 plus 3 times 3, etc., 17,000 times, which gives an inner product of 153,000. Therefore, 200 is negligible compared to that large number. Unfortunately, 200 is still a very large number, and it may be difficult to separate this cluster from other clusters. Indeed, we would like to think of all the users that are essentially the same as the central user up to these random variations, and therefore as one cluster of user. Visually, this cluster may be difficult to single out because it overlaps with clusters of other users. For example, if we consider a user that rates all the movies 3 except for movies about dancing that are rated a 4, if we assume that all the dance movies corresponds to the first columns, the row corresponding to this user would look like this. Now, consider the same type of variations around this user. This is our second cluster. Let's call it the dance cluster. We can create two histograms. The first one that has only the pairwise similarities between rows from the central cluster, that is, variation around the central user, and pairwise similarities between users in the central cluster and users in the dense cluster. In our simulation, we assume that there are 100 dense movies. We can see that there's a huge overlap between the two clusters. In other words, given a user in the central cluster, there are many users in the dense cluster that appear to be more similar to the central user than users in the central cluster. This is a problem. We could overcome this problem by only looking at ratings from movies about dense. In this case, the picture would look like this. The two clusters are very well separated. Moving forward, the main question is how can we automate the selection of dense movies without knowing it? Well, this is exactly the idea of similarity between movies. If they receive a similar rating, then chances are that they are about similar topics, for example, dancing. User item-based recommendation is simultaneously performing this clustering of movies and users. As it turns out, the problem is completely symmetric. I could have told exactly the same story by switching the role of user in items. We have seen that because the problem is so high-dimensional, it might be necessary to group or cluster users and movies simultaneously. This is the subject of user-based recommendations, our next video.